So for the benefit of posterity, we're going to review chapters 3 and 4 for exam 2 for Chem 213. And I haven't figured out how to make this thing scroll. I'm supposed to be able to. I can move the cursor. That didn't move this. Okay. Enough of that. I left my drink in the lab. Don't keep me from talking too much. Okay, so first of all, is there anything in chapter 3 and chapter 4 that's just giving you the willies that we need to talk about first? So I want to do that before we get into anything else. Be sure we get all that covered. No? Nothing in particular? Okay. If something comes up in the middle of our discussion, just holler, stop me. Okay, we have any trouble with this? The naturally occurring copper isotopes exist as these two. The atomic mass of copper is 63.55 atomic mass units. What's the approximate natural abundance of 63 copper? Okay, this is kind of working the weighted average in reverse. Remember the weighted average. And actually, we're going to have to use these values when we know that the atomic mass for these isotopes is not 65 and it's not 63 atomic mass units. That's the total number of protons plus neutrons. That's a number of things. It's not the mass of the things. Relative to carbon-12, these would be fractional values. But since this is a review and possible test problem, we just assume for the moment that this isotope weighs 63 atomic mass units. 63 atomic mass units and 65 atomic mass units. Okay, we need to know the relative abundance. So how did we arrive at this value in the first place? Well, we multiplied this times some fractional value and that one times some fractional value, and then we added the two together to get 63.55 atomic mass units. That's how we got there. So we need to work backwards. The atomic mass, okay, we know that value. What's the approximate natural abundance of this one? Well, we're going to have to use a little algebra. Okay. If we say the natural abundance of 63 is X, okay, what's the natural abundance of this one? Assuming there are only two isotopes. Be 1 minus X, right? Because the fractional abundance has to add up to 1. Did I lose anybody? The puzzle looks. Make that one X, then this one has to be 1 minus X. That's what's left over. Okay, so now we get 63X, and this is 65 times 1 minus X. And these two added together equals that. So there's our formula. We have 63X plus 65 times 1 minus X equals 63.55. Now we can solve for X. And that'll give us the fractional abundance of this one. So how do you convert fractional to percent? Just multiply by 100. Okay, so this one's going to be 65 minus 65, X. And we combine the X's, 63 minus 65 is minus 2X. And this is 65 times 1, of course, 65 is equal to 63.55. Okay? So now we want to get all the numbers on one side and the unknowns on the other side. So if we leave this one here and put this one over here, that means this minus that is a minus. Looks like 1.45, correct? Say 1.5, 4, 10, carry the 1, yeah, 4, 5, yeah, that's right. Okay, now X is going to be this one divided by 2. And since they're both negative, we got a positive number, right? 1.45 divided by 2, which is what? I need my calculator for this. Yeah, I could probably do that one, but I've been burned once already this week. I don't want to do it again. Trying to do math in my head. 0.725. So X equals 0.725, which implies 72.5%. Okay? So the nearest one to that is 70. Okay? Did I lose anybody? Has everybody in here had algebra? Oh, right now, okay. So are you solving equations for one unknown yet? Okay, good, good. So they'll be fresh. And then it doesn't ask for it, but what would be the other one? Well, if this one's approximately 70, the other one would be approximately 30, right? 70, 30. I think the reason that they're saying approximately is so that you don't have to do the exact math. I did the exact math here, but you really don't have to. Just say, what's that close to? This goes into 14 7 times. Okay, so 70%. All right, let me see. When am I supposed to finish the lecture? Because we got a lab to do today. 2 o'clock. No, 3 o'clock. All right. All right. Let's see. I'm gonna have to scroll. I found a laser pointer online that has a thumb scroll in it. So once I get enough money, I'm getting a new pointer, and then I'll be able to scroll remotely. It's treat it like a mouse. Okay, naturally occurring element X exists in 3 isotopes. Right? What they mean here is this would be the symbol of the element, and this would be its mass number, 28. Instead of putting it up here, they put it down there, which is legitimate. That we do that sometimes. And this one, so these 3, this is the true atomic mass unit. Now we're getting the real story. Right? For this isotope, that is its actual atomic mass unit weight for 1 atom of that isotope. And this is its natural abundance, here, 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 and here. What's the identity of element X? What do we need to know to determine X? Well, we have 2 choices, right? We either have the atomic number, which we don't have. We got the mass number. Well, what we need to do is find out what's the mass number. What's the average atomic mass for this element? Then we can probably find it from this chart. But my guess is we could probably get close to it without even doing the calculations, right? Because look here, this one's 92% 27.9. This one's a little heavier, and this one's more, but they're small abundance. So I'd say it kicks it up maybe 10% at max. So 27.9, 28.9, or 29. So which one of these has a mass of 29? Let's see. No. Okay, we're getting warm. It's either silicon or phosphorus. And since the phosphorus is not there, it's got to be silicon. Right? Test taking technique. Get it done quick and move on. Now we could do the calculation. Just weighted average, right? 0.9223 times this one, and then 0.0467 times that one, and 0.0310 times that one, and add them together, and we probably come out with that. Okay. Number 3 is a trick question. The average mass of carbon atom is 12.011 atomic mass units. Assuming you were to pick up only one carbon unit, that being the carbon atom, the chances that you would randomly get one with mass of 12.011 is what? Is there any chance that you would get one with that mass? No. It's a weighted average. That's the average atom, which in reality doesn't exist. 0%. You're not going to find a single atom with that mass. Right? Since that's the standard, you'll find most of them will be exactly 12. And then the 13s will be some 13 point something. Right? So that was the purpose of that question, just to see if you knew what 12.011 means. It's an average atom. It's not a real atom. Can you calculate the mass of 4 atoms of copper in grams? How would we do that? Well, this is dimensional analysis, right? You don't even have to know chemistry to get this one. 4 atoms, and we want grams, right? Okay, what do you need to know to get to grams? What value is assigned to elements that relates grams in any form or fashion? The atomic mass, yes. So these values, we're going to have to use one of these values in here, right, for, what is it? Copper. Okay, so copper is what? 63.55 rounded off. Grams per what? Grams per mole. So this is counting numbers and this is mass. That's counting numbers. So we got to convert this into moles so that we can use this value. So how many atoms per mole? There you go. Get rid of atoms. Now we got moles. Now we can get rid of moles. Grams. 63.55. When I use the conversion factor like that, I write the units in first the way that they need to be. Like I want grams, it's got to be on top, moles on the bottom. And then I take this value and say, all right, which way do I need it? Well, this is the right way, grams on top, moles on the bottom. Sometimes you need grams on the bottom, moles on the top. If you write it this way first with just the units, then you know which way to write it. And you just divide this one into that one times that one. I guess since I don't have the answers, I have to do it. So 4 and divided by 6.022 exponent 23, and then 63.55 times. So I get 4.4 atoms. And this is counting number. So it's, my mind's gone blank. Has infinite significant figures. The example we used in lecture was pencils, I think. So 4 atoms, and conversion factors have infinite significant figures, so we can pick as many as we want. 4.22, how about that? Times 10 to the minus 22 grams. Right here. Okay? Let's see if we need to do this one. A lot of these reviews should be redundant, so we could skip a few of them. I'll tell you what. I should have done this the way I did last time. I've got a copy of. Oh no, didn't do that this time. I usually pick some of these out of here and mark them off so that we don't have to do every one of them. So I guess we're just going to have to fly through here and find the redundant ones and skip those. Let's see. Unit conversions on number 5. Am I having trouble with that one? Okay. Okay. If you have a sample of zinc and a sample of aluminum, and you know you have exactly the same number of atoms in each sample, which of these is true? The mass of zinc sample is more than twice as great as the mass of aluminum sample. What's the comparison that we're making here, actually? If you've got equal number of atoms, what would make the total mass be different? The mass, the individual mass of the atom itself. Right. So we've got aluminum and zinc. So zinc is what? Approximately 65.39 grams per mole, or 65.39 atomic mass units per atom. Okay. We have equal numbers of atoms. So if we just look at one atom, then that'll give us our answer. Aluminum is 26.98. 26.98 atomic mass. This is aluminum, and this is zinc. Okay. So what would that be if we divide this into that one? Let's see. Twice would be about 54. 3 times would be 781 or 82. Okay, so it's between 2 and 3 times. So the mass of the zinc sample, the mass of the zinc sample is more than twice as great as the mass of the aluminum sample. Yeah, it is more than twice. It's not quite 3, but it's more than twice. So that was true. How about this one? Mass of the zinc sample is more than the mass of the aluminum sample, not quite twice. No, that's false. Mass of aluminum is more than twice as, no, that's wrong. Aluminum sample is more than mass, no. Masses are equal, no. So the first one's the only one that works. It's between 2 and 3 times the mass zinc sample as the aluminum sample. So that's one you don't have to do the exact math unless you feel like it. You can answer the question with just estimation. Uh, 43.5 gram sample of ammonia. Right? Do you know what ammonia is? That's the question. You need to know the formula of ammonia in order to answer that question. Ammonia is NH3. Okay, so it'd be 14.01 and then 3.03 for 3 hydrogens. 17.04 grams per mole. And we have 43.5 grams. And we need a conversion factor that will get rid of grams and leave us with moles, correct? How many molecules? Okay. So it's going to force us to use Avogadro's number, looks like. So grams per mole is 17 here, 1 there, and then we have to use Avogadro's to get rid of moles and leave us with molecules. Right, so 1 mole is 6.022 times 10 to the 23rd. Let's see if we can estimate this and get close to the answer. 17 into 43 is about 2, isn't it? And 2 times this would be 12 times 10 to the 23rd, which would be 1.2 times 10 to the 22. Is there one really close to that? 10 to the 22. No, there's not one in there like that at all. I'm calculating. I thought I could estimate my way out of this one. Did I set it up right? 43.5 gram sample. Molar mass gives us mole. 6.022 times 10 to the 23rd molecules per mole. Yeah, that's right. So 43.5 and divide by 17.04. Oh, 2.5. That's it. So D should be the answer. No, D can't be the answer. I went the wrong direction. That should be 24. Right? Because I moved the decimal this way, now it's 24. Right, so D should be the answer. Yeah, 1.54. So sometimes you can get yourself in trouble with estimation as fast as you can with a calculator. All right. So let's see. We don't need to do that one. That's simple dimensional analysis. Molar mass of a compound, you have any trouble with those? Just add up the number of the molar mass for the number of atoms. So this would be carbon times 2 times 12.01, and then 6 hydrogen, 6.06, and then 1 oxygen, 16. Add them together, whatever that happens to be. For which compound does 0.256 mole weigh 12.8 grams? This is sort of a molar mass in reverse, right? Grams per mole. 12.8 grams per how many moles? 0.256 moles. So that value is what we key on here. 12.8 and divide by 0.256 is 50 grams per mole. Okay, how about the molar masses of each one of these? Let's see. That's going to be 24 plus 4 is 28 plus 16. 20, is that right? 20, 16 is 44. So that's not it. How about carbon dioxide? 12 plus 32, 44. How about CH213 That's 12 plus 3 plus 35, 45 for chlorine. So that's 8, 9, 10. 4 or 5. That's it. Right there. This one's only going to be 24 plus 6 is 30. So C is the answer. All right, molar mass of barium sulfite. So you have to be able to write the compound. You having trouble writing compounds? Barium, and then sulfite is what? SO3. 2 minus, and this is 2 plus. That's it. That's the compound. So add up barium, sulfur, and 3 oxygens, and you got it. Let's see. Phosphorus has a molecular formula of P4. Sulfur has a formula of S8. How many grams of phosphorus contain the same number of molecules as 4.23 grams of sulfur? Well, let's do this one. 4.23 grams of sulfur. 4.23 grams. So we need to know the molar mass of sulfur. Like 8 times. Sulfur is 3206 times 8. $256.48. 256.48 grams per mole. That's the number of moles. Go back to the question. How many grams of phosphorus contain the same number of molecules? So this would be the number of molecules. We don't actually have to calculate the number of molecules because mole is a counting number. So this is going to be equal to the number of moles of phosphorus. Right? So how do we calculate phosphorus? Well, this is going to be unknown. Grams. And then we just put in here grams per mole. And then we need sulfur. Set 8 times sulfur, 32. Did I do that one already?
Yeah.
Oh, that's right. I need phosphorus. 4 times phosphorus. 30.97. 4 times that. 123.88. 123.88. Okay. So to solve for this one, you take this one over here. It's the numerator, so it's a ratio of this one to that one times 4.23. Let's see. And you flip it and divide, and then times 4.23. So I get 2.04. 2.04 grams. There it is. Okay. So what we're saying is, if you want to compare masses, and you have the same number of molecules, then all you have to do is ratio the molar masses, and that gives you your multiplier. Okay. All righty. Let's see. Did I skip one? 12, 13. What is the mass of 6.761 mole sample of sodium hydroxide? Oh, that's too easy. Let's skip that one. Atoms of hydrogen present in 6. These are all unit conversions, right? All you have to do here is to find out how many moles of NH3 you have. And then you're going to have 3 times that many hydrogen atoms. Because the ratio is, for every mole of ammonia, you have 3 hydrogens. So 3 times that gives you how many moles, and then you convert moles to numbers. Do I need to set it up? Or are you good? I assume you're good. No response means you're okay. Oh, this is interesting. The molar mass of this compound is. This is a practical application. One molecule of a compound weighs 2.93 times 10 to the minus 22 grams. That's one molecule. We want to know what the molar mass is. So what does that mean? The molar mass is, what's the mass per mole? Right? If we know the mass of one molecule, then all we have to do is convert molecules to moles. Because moles needs to be in the denominator. To be molar mass, it has to be grams per mole. So we just say 6.022 times 10 to the 23rd. There, times that value. And I get 176. There it is right there. That really isn't as practical as I thought it would be. Because who's going to weigh one molecule on the lab? But if your goal is to find the molar mass of a compound, you do need two pieces of information. You need to know how many moles you have of that compound, and then how much does that many moles weigh. Then you can ratio them, that gives you the molar mass. And there are a number of ways you can get the number of moles. Are we going to do one freezing point? No, that's second semester. Freezing point depression. Oh, we're going to titrate an acid and find the molar mass of the acid. Citric acid, I think, is the one we're going to use. So that way, you can weigh the citric acid beforehand and then titrate it to find out how many moles it is. Because you'll titrate it with sodium hydroxide. And then the stoichiometry of the reaction between the acid and the base will tell you, when you reach your endpoint, how many moles of base you used will tell you how many moles of acid there was. So there you have your two items. You have the mass of the citric acid that you weighed out, and then you titrate to determine how many moles. Ratio the two, you got the molar mass of citric acid. You compare that to the accepted value. I'm pretty sure we're going to do that one. Yes. It's lab number 7. So there's a little ways to go before we get to that one. But it's a fun lab. Okay, compound is composed of X and hydrogen. That one there for the next instructor. Now, analysis shows the compound to be 80% X by mass. So this is 80% mass. That means what? This one is what? 20%, right? Mass. Okay. I like to extract the information and put it on the board. Get it away from the confusing language of word problems. With 3 times as many hydrogen atoms as the X atoms. So that means this is actually 3. Which element is X? Okay. So let's see, what do we know about this one? The only thing we know for sure is hydrogen. Right? So if we know that this is 20% hydrogen, 80% X, then the total mass, let's just say we have 100 grams. Okay? If we have 100 grams of sample, how much hydrogen do we have? We have 20 grams, correct? Okay. Then 20 grams of hydrogen, calculator for this one. We could probably estimate it. Is 1.98 moles of hydrogen. So if the ratio is 3 to 1, how many moles of X do we have? Well, 1/3 of that, correct? If this is 3 times that. So we have 0. Let's see. Wait a minute. Let me do that again. No, it's 19.8. Maybe there was something wrong. 19.8. Yeah, 19.8 moles. And then X is going to be 1/3 of that. 6.6. 6.6 moles of X. But how many grams is that? It's 80 grams, isn't it? Right, this is 20, that's 80 to make up 100. Okay, so we got grams and moles, don't we? So we say 80 divided by grams per mole, 6.6 equals what? 80. 12.12. 12.12 grams per mole. Okay, which one comes closest to that one? Carbon. Yeah, it's carbon. Did I need to do that one? Or do you guys, did you already have it? Okay. I don't want to waste your time. I mean, I want to get to the ones that are giving you trouble. But that seemed like an interesting one. So I had put up, what do we know? And then I could start to see a solution develop, because I knew the end game was grams per mole. Yeah. Nitrogen, hydrogen, oxygen, how many grams of hydrogen are there in 153? All right, this just emphasizes, this one right here, emphasizes Proust's law of definite composition. Right. This ratio of mass is fixed for a compound. So if you know the ratio here by mass, then if you have a total mass of a sample, you can find out, oh, let me scroll down. You can find out how many grams of hydrogen there are in that compound. Let's see, what if we add these together? 30, 40, that's 100. Right? So it's 5.05%. And you just take that fraction of this value, and that gives you your hydrogen. Right? 5%. What's 1% of 153 is 1.5 times 5 is like 7.5 or so. There it is right there. Okay. You can do that one in your head. How many grams of potassium are in this many grams of K2CrO7? What is that compound? I think that may be written wrong. It either needs a 2 right here or a 4 right there. And I'm not sure which. Polyatomic ion. Chromium occurs in the only 2 polyatomic ions that I've given you are this one and this one. Right? And it's neither. So there has to be a mistake. I think there is a mistake here. Let me see what the answer is supposed to be. We can figure it out. 29 19. No, 20. It should be 8.98. This one. So maybe we can figure backwards. How many grams of potassium are in 27.8 grams? So 8.98 per 27.8 equals what? So that's 32.3%. Okay. We'll just do one of them. This would be K2 and this would be K2. So let's do this one. What percent potassium is in this one? All right. So 2 potassiums would be 39.101. 39.10 times 2 is 0 to 1867. Right? And then chromium is what? Chromium is 52.00. Then 4 oxygens is 64. All right, so what's the total there? 78.2. Well, you know that twice. Because I want to do them. I want to use that. It's this one ratio to the total. 64. 194.2. 194.2 divided into 78.2 is 40%. So that's 40%, but this one's 32%. So it must be this one. I don't think that's right. This one ought to have less percentage potassium, shouldn't it? Because you got more chromium and more oxygen to balance it out. It ought to be less. So it must be this one. CR07, is that a real? Okay, here's what's happened. This calculation was actually done with that formula. It wasn't using either one of these. That's what happened. So if that one shows up on the test, call me on it and I'll cross it out. I could look, but I'd have to look through every question to see if it's there. If it shows up, let me know and you get credit for that one without working it. Of course, if you work it, then you should come out with that answer or whatever the case may be, using this mass and this formula or some mass in that formula. And you would be able to get the answer. Even if that's not a real compound, it should still work. That's what I get for using somebody else's database. Okay. Then moving along. How about 21? That looks like a brain teaser. A substance A2B has the composition by mass of 60% A, 40% B. What's the composition of AB2 by mass? That give anybody trouble? Didn't give anybody trouble? Or did you get to it? Maybe you skipped over it.
No, I didn't do much of this over the week. I've had a lot of family issues.
Okay. So let's see if we can work this one out. This is our basic, this is our beginning point. A to B is 60% A, 60% A, I need to make a marker. Is there one in here? Yeah. 60% A. There we go. Okay. And 40% B. Okay. What we want to know is what's the composition of AB2? AB2. We want to know percent A and percent B. Okay. Percent is a dimensionless number. If we need to relate two things, we've got to have real masses, for instance. I mean, the fixed ratio is here. See, if you had 100 grams, how many would you have of A? Well, let's see. Let's not look at it that way. Let's look at it. Yeah, that's okay. With 100 grams, you would have 40 grams of B and 60 grams of A. So that means A, out of 100 grams, A is 30 grams each. That's 60 grams of A taken twice, but it's 30 grams of a single A. Okay. Now, if we use that same ratio of 40 to 30 and come over here, then we would have only one A, but two B's for B and A. So 30 divided by 111, is that right? The total here would be 111.
Oh, yeah. 310.
110, excuse me. So that's 27%. So that means this one has to be 73%. Okay, does that get us where we want to be? There we go, 27.73. Yeah, that's the reasoning for that. It's all based upon the definite ratio by mass. Proust, wasn't it? Proust said constant composition. Okay. Each molecule of testosterone contains 19 atoms of carbon with other atoms. The mass percent of carbon in testosterone is 79.1%. What's the molar mass of testosterone? That looks fun. Okay, what are we given? Molecule of testosterone has 19 carbons. So it has carbon 19 plus something else. We don't know what it is. The mass percent of carbon is 79.1%. 79.12% mass for carbon. That means this part of it is what? 20.88, correct? And carry the one, carry the one, carry the one. Yeah. Percent of X left over. Maybe we don't need that, but I'm sort of thinking out loud. Where are we headed? Molar mass of testosterone. So we want the molar mass of this one in grams per mole. So how are we going to get there? Well, suppose we just say, all right, we know we can't work with percent, so we need a mass. What if we just say we have 100 grams Then we have 79.12 grams of carbon and 20.88 grams of whatever else. Okay, so this will give us, let's see, do I need to go this route? Or am I making it more difficult than it needs to be? 19 carbons. If we've got 1 mole of this compound, let's do it this way. I think I am making it more difficult than it needs to be. If we've got 1 mole of compound, then the percent carbon in that compound is 79 point, actually, it's we can do it that way. We got 79.12 grams of carbon per 100 gram sample. Okay. We got to get moles out of here somewhere. How many moles is this? Moles of carbon. Right, if you do have 79.12 grams out of a 100 gram sample, you got 79.12 grams, and 12.01 is 6.59. So this is 6.59 moles of carbon in a 100 gram sample. We got to get to grams per mole of this. If we have 1 mole of this, we've got 1 mole of this, we have 19 moles of carbon. So there's moles of carbon, right, in a 100 gram sample. So 6.91 grams, okay, I can see the end coming. 6.59 moles of carbon. And the ratio is 19 moles of carbon. 19 moles of carbon per mole of compound. Okay, so 19 into 6.59 is 0.347, 0.347 moles of compound per 100 grams. Right, because that was the original. 100 gram sample gives us that many grams of carbon, gives us that many moles of carbon. This ratio gives us moles of compound. Now we got moles of compound and mass of compound. So I just say 100, 288 grams per mole, 88.4. There it is. Took me a while. It's a good thing I stopped going down that other road because I'd have never got there. This is the only way to do it. All right, how are we doing on time? I used up an hour already, it looks like. So we're at 2 o'clock and we need to be finished by 3. Okay. We need to get into chapter 4 pretty soon.
Doing for lab anyways.
Lab techniques. Didn't I hand one out?
You ended up the sheet, yes. It had the Bunsen burner stuff on it.
Yeah, that's the one.
I did the pre-lab question for that. I wasn't sure what to do with that. But over the papers that came with it,
Yeah.
it just explains what would be in the pre-lab there.
Okay. Okay. You guys got a copy of it, don't you?
Yeah. Lots of that.
Oh. It should be in your lab notebook so that you can take your lab notebook and do the experiment with the lab notebook only. That's the goal. Because if you do it that way, that means you've actually read the method, taken time to put it in your notebook. You know the steps already, which makes you a safe experimenter. If you go in and try to treat the experiment like a recipe, then you're just asking for trouble. Let's see. Oh. Substance contains sodium, aluminum, fluorine. No. So it's the mass percent. You can do that one. You can do that one too. Calculate the mass, percent by mass of carbon in this compound. Just add up the molar mass and use that as your denominator. Add up the mass of the carbon, 26 carbons, and divide that by the total mass times 100. And there you have it. There's another one. You have to be careful with these that have parentheses, because this one has 2 nitrogens
And 8 hydrogens.
and 8 hydrogens, correct. Aspirin tablet with a mass of 1 gram burns in air and collects 2.2 grams of carbon dioxide. Water. Molar mass of aspirin is between 170. Oh, this one takes some doing. Did anybody try that one? No. What are we headed for here? Molar mass based upon percent composition, correct? This is the way you would actually do it in the lab. So let's do this. Okay. So with a mass of 1 gram, aspirin tablet, 1 gram is your total mass. Mass. Not in my pocket. That's a brown one, maybe it'll work. Yeah, that works. Okay, so your starting mass is 1 gram sample. No, way down, didn't it? There it is. 1 gram sample. Of aspirin. There we go. So picking that up. Yeah. Okay. You burn it in air. Right, so it combines with oxygen. And you collect 2.2 grams of carbon dioxide. 2.2 grams of CO2. And 0.4 grams of water. 0.4 grams of water. You're also told that it's carbon, hydrogen, oxygen only in this molecule. So if you're burning it in air, you can't determine oxygen from this value. You can't determine oxygen from that value, but you can determine carbon from that value and hydrogen from this one. So carbon, hydrogen, and the oxygen will be by difference, because you know, once you find out the mass of this one, that one, and that one, then that total subtracted from 1 is what's left over is oxygen, right? Okay, so how much of this mass is carbon? Well, we need the mass percent, don't we? Okay, and you can use molar mass. CO2 is what? 12.01 and 32. Is 44.01. 44.01. That's grams of CO2. How many grams of carbon do you have? 12.01. Okay, so that's your ratio of grams carbon to CO2. 12.01 times 2.2 is 6.04. Oh, 0.6004. 0.6004 grams of carbon. How about hydrogen? Well, let's see. Hydrogen's going to be 2.02 grams for every 18.02 grams of water. Right? So we need, let's see, 2.02 enter 18.02. Yep. Divide and then times 0.4, which is 0.0448 grams of hydrogen. Okay, so how many grams of oxygen do we have? We add those up and subtract them from 1. 0.355. 0.355 grams of oxygen. Now we've got our starting point for doing the empirical formula. Remember how I showed you to do that? Well, we're going to need more board space than I got here. So I got to transfer these over here. Zero 0.6004 grams. This is carbon. And hydrogen is 0.0448 grams. And oxygen is 0.355 grams. Okay. Now we can set up our assembly line, Henry Ford style. This many grams is how many moles. This ratio, by the way, is fixed for aspirin. The ratio of mass is fixed for aspirin, as is the number of atoms of each element. That's why the mass is fixed, because the number of elements is fixed. So this ratio is correct. All we need to do is convert it into numbers of carbon, numbers of hydrogen, numbers of oxygen ratio. Then we can determine the empirical formula. That's the first step, all the way to the molecular formula. Okay, so we convert these with molar masses, correct? This is 12.01 grams per mole. And this is hydrogen, 1.01 grams per mole. And this is oxygen, 32 grams per mole. Okay, let's see which one I already have. I've got this one already in there, so I'll divide by 32, which is 0.01109 moles. And this one is 0.0448 divided by 1.01 is 0.04356 moles. Hydrogen. And This one is 0.6004 divided by 12.01, which is 0.04. I'll actually round it off. Okay, I'm going to go on that. 999 moles. So this is carbon, hydrogen, oxygen. Now we need to get whole number ratio, don't we? So which one's the smallest? This one. Right? So we divide all of them through by 0.01109. Same here, same here. This one's going to be 1. This one's going to be what? Close to 4, actually. We'll take that one around 0.01109. Yeah, approximately 4. And this one should be approximately 4 also. Let's check it. About 4.5. Good thing I didn't do that in my head. 4.5. Okay, so we got to get rid of that half. Multiply everything through by 2, right? So this becomes 2, this becomes 8, this becomes 9. So the empirical formula is C9H8O2.
Some of that's.
Huh?
I would like to get that one.
Did I do that right? So what's the empirical weight for this formula? 9 times 12.01, and then add 8.08 for hydrogens, right? 8 times 1.01, and then 32 for oxygen. It's 148. 148 grams per mole. All right. Does that make any sense? I hope I did this right. If it's 148 and the actual, so what we need here is our multiplier. If it's 1, then 148 is right. The molar mass of aspirin between 170 and 190. Right? That's right. None of these. That's what you said, wasn't it? Because if you double it, it's too big. So it should be none of these. Let's see. Did I put that in there as none of these? 27. No, it says, okay, I made a mistake somewhere because it's supposed to be B. Did I do this calculation right? 0.355. Yeah. So if there's a mistake somewhere, I did arriving at these values. That's where it happened. It should be B. So this is probably no, this should be 2. And that would be 4, 8, 9. Yeah, this needs to be 2 already. So I made a mistake somewhere. All right, so we probably ought to get on to chapter 4 in a second. Let me scroll through these and see if there are any that need attention. First of all, do you feel comfortable doing that type of calculation? Once you know the percent composition, you can generate an empirical formula. And then if you know the molar mass, you can jump from empirical to molecular formula. Are you comfortable with that?
Little bit.
Well, the trick is, if you're given the percent composition already, you don't have to calculate it like I did and make a mistake in the calculation. Then you just assume, since percent is a dimensionless number, you assume that if it's going to be parts per 100%, then just make it 100 grams. And that gives you your starting point. The mass composition would be that many grams of each component. And then you work from the molar mass to get the number of moles of each one in the molecule. And you work that ratio until you get all whole numbers. That's the key. That gives you the empirical formula. And then you do that subscript X, you need the multiplier. So you ratio the molar mass to the empirical mass and find out what your multiplier is. And at that point, in that area, it's okay to estimate if you're really close to a whole number. Or if you're close to a half or you're close to a third, you round to that before you did the multiplying to make a whole number. Okay, so we got several examples in there. There's a vitamin C also. Vitamin C is ascorbic acid, in case you're interested. Let's see. Balancing equations. You have any trouble balancing equations? Okay. Usually okay if you use that budgeting method. Did we introduce redox reactions and balancing those? Do the electrons first, then finish it off? We didn't get that far, did we? Okay, that's all right. If we didn't do that, then you don't have to worry about it. Let's see. This one right here, I know that's going to need the fraction trick. Anytime you have a hydrocarbon burned in oxygen, to balance it, you're going to have to eventually use a fraction coefficient as an intermediate step. And then finish it off by getting rid of the fraction. Remember that handout I gave you with the helpful hints? Let's see. What's a stoichiometric ratio? Where you have exact coefficient numbers of each of the reactants and products. Well, if it says the reaction mixture is stoichiometric, that means you need 2 A's for every group. So this one has 1, 2, 3, 4, 5, 6, 7, 8, and 4 B's. That one works. 2, and you look at your selections, 1 only, 2 only, 3 only, 4 only, 1 and 4. Okay, let's see if 4 matches. Then it would be E. So over here we have a stoichiometric ratio. Well, no. Stoichiometric ratio of A and B, that's the question. It says nothing about the products. So it has to be 1 only. Let's see. Stoichiometry, if you know the mass of the reactant, you can find the number of moles of your product oxygen here. 7.11 grams. So how do you get from one point to the other in a balanced equation? Moles is the magic word. If you don't have moles, you can't go anywhere in a balanced equation. So if you're talking masses, you use molar mass and convert to moles. Later on, we're going to talk about solutions. Or is that next? That's the next chapter, isn't it? Yeah, chapter 4. Yeah. If you're going to work a solution problem, it'll usually be in the form of molarity. So that'd be moles per liter. So in that case, in order to find moles, you need both the molarity of the solution and how much of it there is. Right? Because if you multiply this times so many liters of the solution, you know how many moles there are. Maybe we better get on to that pretty quick so we can look at that example. Let's see. Cross that one out. Must have been a massive boo-boo of a question. I was in the wrong place. Oh yeah, limiting reactant. We're still in chapter 3. We didn't get limit. Well, no, we did get limiting reactant in chapter 3. I don't know why I threw that one out. Must have had a good reason. I never throw away a question or a decimal point unless I have to. Let's see. Did I already get into chapter 4? Oh, there it is. There's chapter 4. Okay. So let's look at chapter 4. I need to go get my drink. I'll be right back. My mouth's getting dry. So let's see. Get my bearings here. Yeah, reactions and aqueous solutions. That's what we're after. Okay. All right. Let's start at the top. I can't do all of them, but we'll start here. An unknown substance dissolves readily in water, but not in benzene. Benzene's a non-polar solvent, right? So that this is referencing that rule: like dissolves like. Non-polars dissolve non-polars, polars dissolve polars. So molecules of what type are present in the substance? This unknown substance. If it dissolves in water, they must be polar. They're not non-polar, they have to be polar. All right, by definition, I'm going to scroll. Here we go. The interaction between solute particles and water molecules, which tends to cause the salt to fall apart in water. So what's the process called? It's called hydration. So you're actually forming bonds between the water molecules. And say, for instance, if you had water molecules and sodium ions, where would the sodium be attracted to? Right here. be attracted to the oxygen end. But it's still called hydration, whether it's that or the chloride would end up over here. There's still hydration where you're adding water, that interaction. Let's see. Two organic molecules, ethanol and benzene. One dissolves in water and the other does not. Why? Okay, that's why I gave you the structures here of ethanol and benzene. What you have to recognize here is that the solvent water is polar. Therefore, the molecule has to be polar. You'll notice that all of these bonds around here are exactly equal. That's a clue. This is a non-polar molecule. Whereas this one has the OH, just like water. So it's got a polar part to the molecule here, and that allows it to form a bond, and we call it intermolecular bond between water and the molecule. So why? They have different molar masses? No, that has nothing to do with it. One's ionic, the other's not? No, this one's not ionic. They're both covalent compounds. One is an electrolyte? No. Ethanol contains a polar OH bond, benzene does not. That's the reason right there. All right, all of these are weak acids except which one? Right. Since we've got all selections right here and no funky answers like none of the above or two of the above, then you just have to look at each one and say, which one satisfies as a strong acid? All the following are weak acids except. Well, my guess is this one is the strong acid right here. Any of these halogens will form strong acids right there, there, there. Fluorine is different. And we're not going to find out why until probably, we may be the end of this semester. Certainly by second semester. HF is a weak acid, where HBr is a strong acid. Hydrochloric acid, hydrobromic acid, hydroiodic, they're all strong acids. The rest of them are weak, which means they don't dissociate readily in aqueous solution. They give up a few hydrogen ions, break these off here, 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 and here, but not completely. Hydrobromic acid, yeah, it completely breaks apart. And in that respect, it'd be considered a strong electrolyte too. All right. Let's see, I skipped one, didn't I? Went the wrong direction. Which of the following is, no, that's bad. Which of the following is not a strong base? Right, anytime it's got a hydroxide in there and it's an alkaline metal or an alkaline earth, it's a strong base. So anything lithium, sodium, potassium, rubidium hydroxide, well, calcium hydroxide, yeah, strontium hydroxide, yeah, they're strong bases. Let's see, lithium, strontium, okay, those are all strong. So by process of elimination, this is the only weak base in there, ammonia. Which of these is paired incorrectly? That's a strong acid, definitely. Sulfuric, nitric, no, nitric is a strong acid. That was wrong. That's a strong base, that's a strong acid, that's a weak base. Okay, so this is the outlier right here. That's a strong acid. Man who discovered the essential nature of acids through solution conductivity studies. We didn't talk about this, did we? Come out of the book, probably. the nature of acids through solution conductivity is this guy right here, Arrhenius. We'll see him again. He did more than just mess with acids and conductivity. Let's see. A solid acid HX is mixed with water. Two possible solutions can be obtained. Which of the following is true? In case one, HX is acting like a weak acid. No, because it's completely dissociated, correct? The weak acid is 2. B, in case 1, HX is acting like a strong acid. Yes. Case 2, HX, weak acid. Yes, that's true. And then you can't have both cases the same. HX is not soluble. Well, it is soluble. Okay, so B is the only one that works. How about the concentration? Can you figure the concentration here in molarity if you're given the grams of the solute and the volume? Now, in this case, the reason we're given grams of HF and not volume of HF is that we have to assume in molarity is defined as moles of solute per volume of solution. So if it says we're going to put that many grams of HF in this milliliters of solution, I thought it said grams. Oh, never mind. That's correct. Right. 200 milliliters, 2 times 10 squared, 200 milliliters of solution. All right. So we've got the 200 milliliters, which is 0.2 liters, correct? So what else do we need? We need the moles of HF. So you just need 16.4 grams, and molar mass will convert it to moles. So HF is, let's see, 19 in hydrogen. Yeah, 19, 2001. That's 0.8196 divided by 0.2. That's 4.10. Yeah, 4.1. You just have to pay attention to the formula. What does the formula require? Or what does the equation require? You got to be sure and get the information in there in the right form. What's the concentration of solution B? Oh, they're throwing a lot of blue smoke up in your face with this one. It describes solution A, but it asks about solution B. So you don't even need to pay attention to solution A. Solution B is 2 milliliters of solution A is diluted with 8 milliliters of petroleum ether. What's the concentration of solution B? Well, you have 3. Oh no, it's a sequential dilution. I'm sorry. Yeah, it's a sequential dilution. So let's make a picture out of that. You're starting off with this molarity of solution, and you're taking 1 milliliter of it. So you got 3.50 times 10 to the minus 4th molar of that solution. You take 1 milliliter of it, okay, and dilute it with 9 milliliters of petroleum ether. So it's 1 milliliter per 10 milliliter total. So it's a 1 to 10 dilution. So now the concentration is going to be 3.50 times 10 to the minus 5th. molar. Then you take 2 milliliters of this new solution and dilute it with 8. So the dilution factor now is 2 to 10 or 1 to 5. So 1/5 of this will give you the new concentration. Well, let's see. 1/10 would be 10 to the minus 6. Well, 1/5 would be twice as much as that. So this is going to be 7 times 10. Let's see. This would be 10 to the minus 6. Yeah, 10 to the minus 6 molar. There you go. Is that one of the answers? There it is. That's how I would do it in the lab if I had to think on my feet and figure it out. But you can do it by dimensional analysis, right? You just say this molarity and 1 mil of that into 10, and that's based upon concentrated, diluted, like that. So the concentrated one here, this is the volume of it right there. And then this is the new molarity, which is unknown. And this is the new volume, which is 10 mils. You can do that dilution calculation to get this value, and then do another dilution calculation to get that one. And you should get the same answer. I used to make up standard solutions for a piece of equipment to analyze for elemental composition of plant tissue or soil extracts, whichever the case may be. And the standard solutions were supplied for each element. Many of these elements. In standard solutions, you have to mix up a cocktail in order to standardize the instrument. Well, some of them would be 1,000 parts per million, some of them would be 10,000 parts per million. So you have to know what that means, because parts per million is dimensionless number. And then you would do a dilution in your head. You say, okay, so I need so many mils of this one, so many mils of that one, so many mils of that one, dilute to this volume. Off to the races. Okay. Let's see. How many grams? Okay. If you need to know how many grams of a solute is in a certain volume of a known concentration, you just use that formula. Molarity equals moles divided by volume, and solve for the unknown, which in this case would be moles. So moles would be molarity times volume. But that has to be converted to liters. And then once you got the moles, then you use molar mass to convert to grams. I think we did this one in class, which has the following contains the greatest number of ions. Did we do that one? Let me scroll up. Greatest number of ions. So how many ions does this one have? Molarity times volume equals moles of the compound. But what happens in solution? It breaks up into 2 ions, doesn't it? So this would be 0.1. And did I show you the trick? If you multiply molarity times milliliters, you get millimoles. So 0.1 times 40 is, 400 is 40 of this, but 80 of ions. So this would be 80 millimoles of ions. This has 3 of them. 1, 2, 3. So this would be 30 times 3 would be 90 millimoles. And this one would be 4. So 0.1 times 200 is 20, times 4 is 80. And this one is 1, 2. So that's 0.1 times is 20, times 2 is 40 millimoles. And this is sucrose, which does not dissociate in water. It makes no ions. Well, that was out. So which one makes the greatest number? This one. All right. Let's move on from these dilution problems. I think we've got those well in hand. You have two solutions of sodium chloride. One is 2 molar, the other is 4 molar. You got much more than 4 molar solution, and you add the solutions together. Which of the following could be the concentration? All right. So let's think about this logically. If you've got much more of the 4 molar than you do of the 2 molar, let's think about it this way. If you added equal volumes of 4 molar and 4 molar, you still have 4 molar, right? So if you had equal volumes of 4 molar and 2 molar, what would you have? 3 molar, right? Halfway in between, if equal volumes. But if you've got a whole lot more 4 molar than you do 2 molar, then the value is going to be really close to 4, but not quite 4 because you're diluting it with a lower concentration. So it's going to be less than 4. That means this one's out and this one's out. And this one is too low. It's got to be really close to 4. It's not going to be 3 because it's not halfway in between. That would be equal amounts. So 3.5 is the only answer that works for this scenario. All right. Let's see. That one could be fun. Anybody try this one? Number 23. Let me scroll down and see how many of these we've got. Oh, we got a lot. Okay, let's not stop on that one then. Let's go down. I'll tell you what, let's work from the bottom. Work away. Balancing equations. Okay, those are balanced equations, balanced equations. Fill in the blanks. Okay. We got into formula equation, balanced formula equation, complete ionic equation, and net ionic equation. Did we do that? Not sound familiar, does it? I thought we would have got one like that before. Okay. Ooh, we did get some redox equations. Okay, so let's see. Can you okay, here we go. Recognizing what type of equation it is. Okay, let me be sure I'm not. Okay, let's go back down. Pick those up where they start. Oxidation states. You have trouble figuring oxidation states. You need to do oxidation states correctly in order to tell whether the reaction is oxidation or reduction. Quantitatively. Qualitatively, we have a couple of options. If your reaction is with something reacted with oxygen, that's a combustion, but it's also an oxidation reduction. If you have an element on this side, say, you have an element here, reacting with a compound, B, C, right? And this thing ends up in a compound on this side. That's oxidation reduction. Whenever you go from element, which is always zero oxidation state, it's going to have a different oxidation state. That is oxidation reduction. So that's the quick qualitative way to determine whether you have a redox reaction. Now, that's not always the case. Those clues may not be there. If they're not there, then you have to do the oxidation states and determine. So the first thing you have to do is follow the rules and find out what the oxidation number is for each element in your reaction, and then compare them. So what do we say about oxygen? It's always -2. Let's write it bigger. So this is -2, and hydrogen's +1. So that means this is -6, and this is +1. So you actually -5, that has to be balanced by nitrogen. So nitrogen is going to be +5. Let's see. No, that's not it. That's +5, can't be. We won't answer the question. How about the next one? Oxygen's -2, you have two of them -4. That's it. This is +4. Okay? And since we don't have two of the above or any of those squirrely answers, once you find the answer, you just put it down and go to the next one. Let's see. How about this one? Which of the following statements is not true? When a metal reacts with a nonmetal, an ionic compound is formed. Oh yeah, that happens all the time. A metal-nonmetal reaction can always be assumed to be oxidation reduction. Yeah. If you start with elemental metal and elemental nonmetal, when they react, they always oxidation reduction. Two nonmetals can undergo an oxidation reduction reaction. Oh yeah, that's possible. Right. All you have to do is say methane and burn it in oxygen. Right. Carbon, hydrogen, oxygen, they're all nonmetals. When two nonmetals react, the compound forms out. No, that's false. A metal-nonmetal reaction involves electron transfer. Yeah, that's true. So D is the false one. You don't get an ionic compound from two nonmetals. Nonmetals tend to accept electrons, and metals tend to give them up. As a general rule. Okay. How about this one? Which species is oxidized? So what is oxidation? Oxidation is loss. Reduction is gain. So who loses electrons here? Well, we have to look. This one's 0. This one's 0. So over here, this one is -2, and this one's +2. So calcium had to lose electrons. Calcium is oxidized. C is the answer. It's oxidized. All right. Let's see. I was looking for recognizing reactions. I thought we had some in here. No, it's not. Let's see if we can. I saw one in here that I'd like to do. Balance of reaction. Oh, here we go. Identifying oxidation. Oxidizing agent, reducing agent. Remember, an oxidizing agent causes oxidation, so it must be reduced itself. And vice versa. A reducing agent causes reduction, so it has to give up electrons. It means it has to be oxidized to do that. Let's see. Balance the following oxidation reduction reaction using oxidation number method. Okay, this one should be fairly easy. So if we have Fe 3 plus combined with I minus and makes Fe 2 plus combined with I 2. Balance that. Now, you can probably do it in your head, but let's do it the oxidation reduction method. So we need to find out. Iron went from 3 plus to 2 plus, which means it gained an electron. So that's gain 1 electron per iron. That means this one had to be reduced. So iodine went from -1 to 0. It lost an electron. So loss 1 electron per iodine. But we got 2 of them, right? So that means 2 electrons had to be lost to get to this point, which means we need 2 of these, right? 1 electron each went from -1 to 0, okay? So now, if we've got 2 electrons that were lost, we have to have 2 electrons that were gained. There's no other way. Times 2. So times 2 means we need 2 of these and 2 of those. Okay? So it should be balanced now. Oh, by the way, if you don't do this by the redox method, right, you won't get 2 irons here. If you just do it by our normal inspection, we would say, oh yeah, we need 2 iodines because there are 2 over here. But it doesn't say that we need 2 irons because we've got 1 on one side and 1 on the other. But if you consider the electron transfer, you have to have 2 here, 2 here. All right. So let me, in the remaining 8.5 minutes, let's see if we can find a different one. Scroll. Oh, okay. This one might be a bear. Let's come back to 65 if we have time. Oh, okay. Here we do have, yeah, net ionic equation because there's a mention of spectator ions right here. That means we had to discuss in that chapter. So what are the spectator ions here? Well, you have to look at the phases of each one. If this is in an aqueous solution, all nitrates are soluble. So you got lead and nitrate on this side, ions. Potassium salts are soluble. So you've got potassium-free ions and chloride-free ions. On this side, we've got a solid right there. Lead chloride is a solid, lead 2 chloride. And you just need to look in that chart right here. And so if we follow along here and find lead way out here, then go down to chloride. There it is. It's grayed out. So that means it precipitates. So that means this is, we keep this in the net equation. This ion, 2 plus, that's 1 minus, this is 1 plus, that's a minus. This is a solid, and this is a plus, and this is a minus. So there's potassium on both sides, that's a spectator. Right? So it's either this one or that one. And nitrate is a spectator. So it's this one right here. Sometimes I like projecting on a whiteboard like this. My Greenbrier, Lewisburg class is like that. At Beckley, we project onto a screen, so I can't write on it. This is nice when I can do that. Okay. Identify the precipitate. What do? It's a double replacement. You just swap ions. Swap iron with carbonate and ammonia with nitrate. We know ammonium nitrate is soluble. And we look up iron and carbonate and find that it's insoluble. That's your precipitate. Oh, but we got to write the correct equation. All right, so what's the charge on this one? That's 2 minuses. That has to be Fe2 plus, and that's 2 minus. So it's just one of these and one of those balances charges. So it should be this one right here. Okay. Balance this equation. Oh, that's interesting. You know what that is? Right here. It's nitroglycerin. Let's see. We got 5 minutes left. We'll come back to that one. It's a fun one if we don't find something better. Let's see. So if you're going to balance an equation like this, you notice that that's a -1. And then this one is a 0. So that should give you a clue. You probably want to use oxidation reduction to get started. Maybe we better do this one. That'd be a good example. What else? That's the last one. Okay, let's do this one and then we'll go in the lab. So if we have Ki plus HNO3 yields KNO3 plus NO plus I2 plus H2O. I hope I didn't bite off more than I could chew. The reason I say that is we got nitrate on this side. We got nitrate here, but we also got split it out. We split out some nitrogen there in another molecule. So that complicates things, which means that we probably need to do the redox, balance the electrons first, and then go after the atom balance. So let's do that. This is a -1. This is a +1. This is a +1. This is 2 minus, so that's 6 minus, and a +1 is 5 minus. This is +5. Okay. This one is same thing, +5 minus 2 plus 1, right? Because that's a plus, this is a plus, that's a 2 minus, has to be +5. No other possibility. This one is -2, so this one's a +2. And this one is a 0, and this one's a -2, and this is a +1. Okay, so now we got all our oxidation states up there. We'll say, what happens where? Potassium didn't change. Iodine changed. So iodine lost an electron, lost 1 electron per iodine. Okay, how about nitrogen? Well, some of this nitrogen went from here over here. +5 to +2 means it gained 3 electrons for nitrogen. So gain 3 electrons per nitrogen. But only some of them did that. Some of them were untouched. They remained here. So let's balance it out. This is going to have to be at least 2 electrons. So this is already 3 electrons. So how do you balance 3 against 2? You cross multiply. So we need to balance, we need to multiply 3. Let's see. I didn't multiply this yet. 2. So that's 2. 2 like that. Now if we multiply 3 times this, 2 times that. So 3 times this would be 6. and 3. And then 2 times this one comes from that 2. So we need 2 here and, oops, excuse me, and 2 here. Okay, so that should give us times 2 equals 6 electrons, and this was times 3. We had 2 already, but 3 times it would be 6 electrons. Okay. So now we're balanced in electrons. This is our new starting point for balancing the equation with a budget. So from here on in, we're going to work like that. And let's see, let's replace that with a 6. And that one's a 3. So let me move this out just a little bit. 3 iodines. There we go. So now we can do our budget. Since we broke up here, no, we are going to have to do that. We're going to have individual potassium, iodine, hydrogen, nitrogen, and oxygen. Okay, so potassium's on this side, we got 6. Iodines, we got 6. Hydrogens, we got 2. Nitrogens, we have 2. And oxygens, we have 6. On this side, we have potassium, 1. Iodines, 6. Hydrogens, 2. Nitrogens, 1, 2, 3. And oxygens, we have 1, 2, 3, 6. Okay. Now, where to start? If we do potassiums, let's see, are there any elements we hold? We might hold this one till last. But it's also on both sides. We've already got 6 iodines, so we're probably not going to touch that. Let's start with potassium. Just start at the top. We need 6 potassium on this side, don't we? 6 potassium. What does that do to nitrogen? 6, 7, 8 nitrogens. Okay? But it also gives us more oxygen. 3 times 6 is 18, 19, 20, 21. Okay? Now, how about nitrogens on this side? We need 8 total. So if we multiply this one, make this one 8, or increase it by 4. 8. So now we have 8 nitrogens, 8 hydrogens, 3 times 8 is 24 oxygens, 4 oxygens. Okay, that one, that one, that one. These 2 are off. So we need hydrogens, right? We need 8 hydrogens over here. That means 4, 5, 6, and 6 and 18 is 24, right? We're done. There for a while, I didn't think we were going to get there. It was pretty complicated. But if you don't do the redox part of this first, then the chances are you're never going to balance it. So if you recognize a redox reaction, start with the electrons. That was pretty hairy. I hope if I gave that one like that to you, it was a bonus. If it takes me that long to do it, I can imagine how long it would take you. The rule of thumb